Hello, my name is Mick Wolbers, and this will be a short video explaining what I did in my thesis, the methods I've used, and the findings that I've found. My thesis was about studying the time variation in tradable vector risk premia. Tradable vector risk premia are a specific kind of risk premia. First of all, let me introduce what vectors are. The first known vector was the market vector, which captures how much a certain asset moves up and down with the market. So an asset that will be moving with the same amount up and down along with the market would have a beta of 1, which will mean it's market neutral. In that way, you also have companies that have betas or assets that are priced with betas higher than 1, which means they move more up with market and down with market. So for example, a beta of 2 means that the moves are 2 times as big, like positively correlated. And the beta of 0 would indicate that a vector, like an asset, would be priced irrespective of the market. It is not correlated at all between something. Beta coefficient of -1 would mean it's inversely correlated, perfectly inversely correlated, an average. So that will be super helpful. Well, there are way more factors than only the market factor. And in this thesis, we are going to study a multitude of them. So we have the momentum factor, we have the standard short-term reversal factor, and like a lot more. Like there are now more than 50, 100 like factors, super easy to come up with. So yeah, there are more and more. And that also brings us to a big problem, because how can you select the best factor? Which factor should you use for your model? Well, that's difficult. And especially difficult once you're making a time varying model. That's what I did in this thesis as well. I made a time varying model where in each period I want to choose only the right factors, right? Yeah. So before we go to these exciting graphs, first let's give some context about that. Because let's go to the beginning. We'll see the title of my thesis: Time Variation of Vector Risk Premia. Yeah, the contents. Yeah, here's some introduction, right? About how they got introduced, because the tradable vector risk premia were introduced in this paper. And they define the tradable vector risk premia, as we will see later, which is a super helpful way of constructing the risk premia, since they only depend on the asset and vector returns, which are easy to obtain. So, blah, blah, blah. Some literature review, of course, on how the vector models came into existence. And then we go to the nice part, which is the methodology. First of all, we'll see how the tradable vector risk premia are calculated. Well, we first define the conditional moments, which are necessary in order to calculate the tradable vector risk premia. Well, here you see the conditional moments of the mean, variance, and the covariance matrices. With those conditional moments, we can then calculate the tradable vector risk premia for every time t. And they are defined by this matrix computations. Well, and then already you have it. You have your tradable vector risk premia, which is time varying. Super interesting. Here on, I will explain a bit more on how they are constructed using the stochastic discount factor. I mean, that will be a bit lower than here. So yeah, this is just some background information. And then we move on to the Oracle estimator. The Oracle estimator is super important in this analysis, since it determines when and which factors are said to be active in that time period. And with active, I mean they are economically relevant. They are not irrelevant, and they're also not weak. So for that, we also need some covariance matrices and variance matrices. And first of all, we want to define a time varying correlation matrix, which is defined as this. With that matrix, we can then compute the Oracle estimator, the Oracle risk premia at every time. So the Oracle risk premia for a specific vector is defined by this. It's the sign of the tradable vector risk premia for that vector times the maximum of either this expression or 0. Looking at this, we see that it's the tradable vector risk premia subtracted by a penalization amount. This penalization depends on the tau that is chosen, and the correlation coefficient, of course, and the squared norm, which means it's always a positive number. So this will always also be a positive number. So we always subtract a positive number, which means that always the oracle estimator is smaller than the risk premia for the tradable factor risk premia. And 0 is the lower bound. So it can never be more, or it can never be lower than 0, because we choose the maximum of these two. This computation ensures that only factors that are not weak and not irrelevant stay in the model. Only those factors. So we can do this for every factor, and then every time t as well, to obtain the time varying estimates of all the factors, where the factors that are weak or irrelevant for a certain period are set to 0. In this equation, the value of tau is very important, because this value of tau is chosen in such a way where it determines how much penalization is applied to this factor. We need to be careful about choosing this penalization, because of course, if we put it at 0, it's not going to do anything. If we put it too high, it's always going to shrink the risk premia towards 0. I mean, almost always, of course, and as long as it's not 0. So what we do, like big part of my thesis is choosing the right amount or the right value for tau. Well, that we'll do like based on a generalized cross-validation method. And I will quickly explain here how that works as well. Yeah, basically a generalized cross-validation method works as follows. In the top of the equation, we have the bias in the mean. So it's a mean variance bias, right? It's a trade-off. We want to be that the estimated returns are close to the real returns, and at the same time we don't want to have too many factors included in the model. So it's a trade-off. In order to calculate this GCV, we first need to come up with a time varying beta coefficient for only the active factors. That's necessary. So with this notation, I made sure that we only are accounting for the active factors. So we're looking at the covariance matrices of the factors and the returns, and then we're only calculating the betas by only looking at the rows of the active factors. So and that's why we see the covariance matrices, and it's only the covariance matrices here that have been applied, or like the columns have been deleted, which of the factors that have been set to 0 in that time period. And then we obtain the time varying beta coefficients, and with that we can also calculate the estimated returns, right? Because what we do, the estimated beta coefficients, we multiply by the oracle time varying risk premia to obtain the estimated returns, right? I mean the predicted returns. And then we subtract that from the actual returns at time t. Yeah, and the actual returns are there as the conditional time varying means of the asset returns. So it's a rolling window kind of. It's more like what we'll see later. This is not dependent on only time t, but also on the past observations. Yeah, we divide by 1 minus s. S is the amount of active factors during that time, divided by t. So that will mean that when s is higher, right, this will be bigger, and hence this will be smaller. So we'll divide by a smaller number, which means that the total will be bigger. It's negative for the GCV because we are wanting to minimize the GCV. That's what we do, and doing that gives us an optimal value for tau, which we'll see in the estimation section. Because we want to look at the time varying risk premia not on itself, but also compared to other risk premia, we'll also introduce 2 benchmark methods. First of them will be the conditional Fama-Macbeth risk premia, which is like a simple first estimate of the risk premia. It's made from It is derived from one of the most influential first papers on risk premia, which is based on the classical two-step procedure of Fama-Macbeth. Yeah, well, the way you can calculate it, also only using matrices, is this. First, you need to estimate the beta coefficient, which can be estimated like this, time-varying way, so it's conditional. And then with those estimated beta coefficients, you can then calculate or estimate the time-varying Fama-Macbeth risk premia. Well, it's nice for comparison. And of course, also, again, if we want to see what would we expect with the returns in the period t+1, we can again multiply the beta coefficients by the time-varying risk premia estimates of our method, this case. Then another method that's being introduced mainly to solve certain problems of the Fama-Macbeth method is the misspecification robust estimator. It's developed by Khan in 2013 with his colleagues, and also applied in this paper. Summarized, we can calculate these risk premia, the Khan-Rabuti-Shanken risk premia, the misspecification robust, as this. Okay, and we need a beta estimate, which we already calculated before, but also there is a weighting matrix here. This weighting matrix ensures that we are optimizing the weightings in such a way where we are less dependent on the less relevant factor. Well, then we look at a quick comparison of how the stochastic discount factors or how the risk premia are constructed using the stochastic discount factors in the different assets. And first of all, we get a bit like the most essential known equation to start with. And with that, we can price the general, or we can write down the general definition of the factor risk premia as the negative covariance of the factors with the stochastic discount factor. Well, if we want to do this for the tradable factor risk premia, we are doing this, we are estimating this. Let me see, we are estimating this risk premia. Here, we're estimating the stochastic discount factor. Yeah, that's what's happening here. We're estimating the stochastic discount factor in this specific way. So the difference in methods mainly depend on the way how the stochastic discount factor is being estimated. And for the tradable factor risk premia, and also then the oracle, of course, we base it on the factor returns, asset returns, on the excess assets returns. So what we see here, this stochastic discount factor is spent on the asset returns, right? Because we look at the returns and the mean return to see what is this value for the stochastic discount. Again, also there's like a weighting factor here on this place. And it's actually the one, the weighting where the Sharpe ratio is maximized. And then this will give you the stochastic discount. Well, plugging this into the general equation will then yield us this, which gives us the expression as we saw before. Well, the other two methods, they depend on a bit different stochastic discount factor, namely, it's now spent on the factor returns instead of the asset return. Here we are spending it on the asset returns. Here we are spending the stochastic discount factor on the factor returns. Well, this yields in a different model and also with different properties depending on which data you use, as we'll see later. We know the weighting matrix. Well, this is all more technical, but again, applying this, taking this stochastic discount factor and putting it into the formula for risk premia, in the general formula, we obtain again the Fama-Macbeth risk premia, like we found before, but also the misspecification robust risk premia, which were a bit too long to include here, but it's the same as what we saw before. So the way we are estimating the conditional moments, as we started with, is done using Gaussian kernel smoothing. So it's also good to go over that. What Gaussian kernel smoothing does, it is kind of like applying a rolling window where you look at the past X amount of observations and then estimate the mean, variance, and covariance matrices. But instead of using an exact rolling window, all the past observations are weighted equally, we are now looking or applying weighting where the observations closest to the current observations are weighted more than the observations more far away. So in that way, we'll see a picture soon. We can give all observations still relevance, but we decrease that relevance as we move further along the past observations. So we move further along back in time. That's what it does. But again, it brings some things we need to be aware of. First of all, the bandwidth selection, because what do we want to choose? Like how many past observations do we want to include into calculating the conditional moment? That's an important question. For that, there are specific methods you can use. You can use a rule, the Silverman's rule, for example, to come up with a rule of thumb, like for our first example. So you can plug it in. It has some downsides, as I described here, because it gives you a value, but it's a very general estimate and it doesn't look at your data. So to refine that method, we also look at a cross-validation method. And what it does, it looks at the error of the estimated returns using the kernel, So we look at only the first moment here, the mean. We try to estimate the mean by looking at the past observations as applied on the kernel. So the kernel says this is the weighting for the past observations. And then we look at per bandwidth h, which gives us the lowest mean squared error. So what is the lowest error we can get for estimating these next step returns, comparing to the actual returns. So we minimize over h, the mean square error over h to get the optimal value for h, and that, this is something extra that will result us in a graph where we can see, okay, this is the mean square error, and it will be the lowest here or here. Same, we also have a problem with the burn-in period because we are burning in periods, right? Because the first 100 periods, for example, what I chose here, you cannot calculate the conditional moments because if, for example, you put the Gaussian kernel method on a bandwidth method of 100 or more than 100, actually you first need to burn the first 100 in order to get a reliable estimate. Because if you're going to calculate it for the fifth time period, you only can use 5 past periods. That will give you very volatile estimates. So that we don't want. So we burn 100 periods. The choose of kernel, again, is being tested by comparing it to other kernels, which we'll see later. But yeah, what I use is a Gaussian kernel, and this is how it's being calculated in the unnormalized version, which is I use. And this will give us the weight. This will give us the weights for every time t, I, and the bandwidth choice h. So now we move on to estimation, and we'll see how we actually calculate the time varying moments. These are the first moments of the returns and the vectors, and then the variance covariance matrices. What we see, we just calculate them in a normal way, but then we apply the Gaussian kernel by giving current observations more weight than past. So, well, what we already said, we want to select the optimal bandwidth, and like the formula I showed before, we can plot this mean square error over the different bandwidth. So in my statistical program in Python, I calculated the mean square error for all the different bandwidth, and then we can obtain this graph. And what we see here, the MSE is minimized at a bandwidth of 200, but also is already quite low at 100. And because we are only not have so much data, we already choose this value of 100, right? Because it seems to be the same. If we go back more, then it gets volatile, and that's what we don't want. But the difference here is very small. well, here again are the different ways to calculate all the risk premia, the time-varying risk premia used in this thesis. Asymptotic distributions we are not doing here, but we can refer to their respective papers. And also the selection of the penalization parameter tau, what we talked about before as well, is being done here. What we do is we do the general cross-validation method for every time t. And at every time t, it will give us an optimal value of tau. What we see is that that optimal value of tau is almost always around 0.1. But some periods it shoots up. So that's quite interesting to see. Yeah, so that's what we did. Then we have a choice. What do? We choose a static value of tau, or we choose a time-varying value of tau. I choose to have a static value of tau since it is quite static as it seems. It seems to be around 0.1. And also when we calculate the expected returns based on this tau, based on the tau chosen, then we calculate the oracle risk premia. And then we apply that to the beta representation to obtain the expected returns. We see that for normal risk premia that are activated, the difference is not so big. Choosing a tau of 0.0, 0.1, 0.5, 0.9, these are the difference, and the dynamic tau is the blue line. We see it mostly hovers, the blue line mostly hovers on the static tau value, but sometimes goes below it. That difference is almost insignificant. For a factor that is not deemed relevant by the oracle estimator for all static values, still the dynamic value we obtain makes that the risk premia shoot up. They're still almost zero, but yeah, they become sometimes non-negative or non-zero, which we do not want. This seems a bit like, yeah, this seems weird. So that's why we choose to have the static tau of 0.1. Here as well, we look at the asymptotic behavior of tau. We see that the tau goes to 0 as t increases. And here it goes to infinity, like squared or not squared. T goes to infinity, which is also shown by this table. So the data we use in this study, for the rest, is two data sets. First data set is the data set which is the long horizon data set. In this data set, I try to find factors which spend the most amount of time possible, because it's interesting, right? Since we're looking at the time variation in risk premia, we want to look at a very long time period. The longer time period, the more we can say about economic recessions, about weird periods where things happen, etc., etc. So that's what we do in study 1. It goes from 1927 to 2024, so it's also very recent. And in study 2, we look at a study with a lot of factors. So here we only use 5 factors, which are these. And study 2 uses the data set of the paper of Svetlana Iskovana, and they use 51 factors. And they also have non-tradable factors, which I don't have in the other one. 17 non-tradable and 34 tradable factors. So that's quite a lot more. And we also have some macroeconomic variables in this thesis, since we also want to test the cyclicality of the premia. Are risk premia, are they cyclical in their behavior, like with the macroeconomic conditions? So having this data, we can now already obtain the empirical results. Well, this is still from the data section. Because what we first do is we look at the performance of the estimated risk premia compared to a rolling window approach, which is actually really testing the Gaussian kernel. Is it a robust way of calculating the conditional moments, or is a much simpler way of calculating those moments better, like a rolling window approach? A rolling window is very easy. You take current observations, you say I want the 100 last observations, and you all give them an equal weight, right? Instead of a decreasing weight, it's with the Gaussian kernel. Yeah, that's what we did. We looked at the different graphs of the risk premia calculated using the different kernels. This is the exact same risk premia, but then for the Gaussian kernel and the uniform kernel, the Gaussian kernel gives a bit of more flat space. Okay, so well, they look quite similar. It's a bit different. What we do to see which is actually the best, again, we look at the returns, the estimated returns. but now using the beta representation. So we look at the estimated betas and we multiply them by the estimated risk premia to obtain the estimated asset return factor. Then we subtract those to get the errors, and then we again calculate the mean square error of and expect the return estimated by the beta representation compared to the actual return at that time. So then we obtain this. What we see is that the Oracle risk premia, it always outperforms because it has the lowest mean square error for all of the different methods in the Gaussian, but also in the uniform. Then if we compare the Gaussian to the uniform, we always see that the Gaussian obtains lower mean squared errors, which is positive. And what we also observe is that as the bandwidth goes bigger, also the mean square error decreases. So, and what we learn, bigger bandwidth better. Oracle risk premia always the best. Gaussian kernel actually is a good method. It outperforms the uniform kernel, which is another name for the, not another name, but it's a rolling window. In our case, is actually a uniform, which I also show in the paper. So it's good that we choose this one. It's a confirmation, and it also shows us all these other interesting points. Then we also look at what's the impact of the different values of tau in the mean square error. And what we see is that actually our chosen value of 0.1 for the tau parameter is too little. Because, I mean, not too little, but according to the mean squared error, it would be better to choose a tau of 0.6 for the Gaussian kernel. And that penalizes more, but by penalizing more factors, we actually obtain a lower mean square error. That's an interesting finding. So that is this section. Then we go to the comparison of the different risk premia. Here's where it becomes juicy, because here we can actually see how these risk premia, they vary over time and what the different methods yield in different risk premia. So we first look at study 1. We see at the table how much the mean and standard deviations are, and also how much does the Oracle think the factor should be inactive. And the market factor never inactive, but the short-term reversal factor should be inactive for more than 50% of the time, it says. Here we get the first plots, right? The different methods with the different colors, and the risk premia vary. Risk premia go up, go down, go up, go down, go up. And so we see they're not static, and they are changing. At some periods, for example, this is the market factor, the risk premia is higher for that, and sometimes it goes lower, and sometimes it's higher again. So assets that are more exposed to the market factor, they are performing better here than they would be performing here. Well, then we look at some other factors. Here we see like very erratic behavior of the different methods. The Oracle estimator determines that the factor is almost zero all the time, while our benchmark methods produce wild results, like big difference. It shows us that we might are having a very good model here that determines correctly maybe that this is all noise. For study 2, we did the same, and what we actually found is by looking at 51 factors is that we could all group them in different groups based on the characteristics. In some of the groups, they are not here, the pictures. Oh, yeah, some of them are here. In some of the groups, we see that the Oracle is always zero, while the FM and the KRS are non-zero, but very small. Sometimes the Oracle does become non-zero, but it's also very small. Tradable factor risk premia, Oracle, and KRS. No, not Oracle. The other three are here. Or we have a picture where all of them are actually non-zero, like here. Then we can also have this case. In the paper, it will be better to look at and discuss them case by case. Then we quickly look at the overlapping factors of study 1 and 2, which is interesting. And then we look at the risk premia and the business cycles. How are risk premia related to the business cycle? First, this is a regression we are doing on Hadoop. Risk premia regressed on the macroeconomic variables. These are the simple correlations between the risk premia of the tradable factor risk premia and the oracle risk premia with the different factors. Multivariate regressions on the market risk premia, and what we also try to do is to predict the next period risk premia based on the current macroeconomic variables and what they are shown in the appendix, the regression results. Persistence of risk premia is then there because with that oracle estimator we can see how many factors are being set active at each point in time. This plot depicts that. It shows you how many factors are active. It goes up, it goes down. Not many factors are needed here, or not many factors are relevant. Then apparently more are relevant, and then less are relevant over time. We can think about reasons for that as is done in the paper. These are the factors. When are they active? So the specific factors. We see that all the white periods means that the factor should be active by the oracle estimator, and all the black periods says that it shouldn't be active. Some factors, they become never active, and some factors, all the white ones, they are almost always active, and some of them are always active. Well, some conclusions about that, and then the conclusions of thesis. And what we find is that modeling time-varying risk premia is good to do it in a time-varying way, the risk premia, to model them in a time-varying way. We also saw, we see evidence for that risk premia are actually cyclical in nature with macroeconomic variables. We see that the oracle method outproduces the other methods in the way of the mean squared error estimate of the out-of-sample predicted returns. We see that a Gaussian kernel can be very helpful in also calculating the conditional moments, and also outperforms in the mean squared error returns. So all in all, it's a very helpful thesis, and it contains a lot of nice graphs about time-varying risk premia, which an investor, of course, can use to determine, okay, which factors are actually the factors that I should be looking at right now, which are could be most profitable. Well, here are some future research options I mentioned, which could be done for future research, and appendices. This is what I wanted to show for the Gaussian kernel. This is what the Gaussian kernel does. I choose the one with HS100, which means these are the past periods, and this is the weighting. So one period back will receive a weighting of 1, while 150 periods back will receive a weighting of like a bit more than 0.3. The correlation heat map of the first factors, these are the industry portfolios used. Another correlation method, the rolling correlations in study 1. These are the correlation heat map for study 2. These are the factors used for study 2, and the non-tradable, tradable. These are the asset returns in study 2, along with the tradable factors of this list. The oracle, many factors the oracle sets active over time in study 1. And these are the other risk premia estimated. And these are some robustness checks to see what is the different applications of different choices of tau on the amount of active factors in the first study and then in the second study. And of course, the higher we make tau, the lower the amount of the active factors chosen, because more factors are being penalized, right? Because here at the top is 24, here at the top is 14. Well, here are some more summary statistics of the risk premia, and here is a graphical representation on what the implications are for choosing a different bandwidth value for the Gaussian kernel estimation. A bandwidth of 20 shows a very volatile behavior of the estimated risk premia, while a bandwidth of 600 shows a very slowly moving risk premia estimate graphs. These are the other kernels we could use, also with their mean squared error minimization here, right? We see that the Gaussian kernel was minimal at 200 with what we saw before. The other kernels, they have higher minimal or minimized mean squared error bandwidths. These are the risk premia calculated with the different kernels. What we see, there are a difference here. This is the one we choose. These are the ones we didn't choose. And this is also for another setting of tau. And higher tau, so more black periods. The factors are less active, set less active. Some more plots. These are the comparisons between studies using the different data, because these are the overlapping factors. What we see is study 1, study 2. The market factor seems quite overlapping. S&B factor a bit. These become very different. So magnitude and in shape, and even more so for these factors. And the analysis why that happens is in the thesis, which is quite interesting. And then some rolling mean squared errors of the different methods, which are overlapping. And these are the regression results for the univariate regressions of the market risk premia on the different macroeconomic variables. We see they are all statistically significant, but when we combine them, we actually see that model of only a credit spread, unemployment rate, and a constant already has an R squared of 0.7, which doesn't improve as we, almost doesn't improve as we add more variables. And these are the regression results of the out of sample regressions, where we try to predict these risk premia based on these factors, and they're all univariate. So this on this, this on this, this on this, this on this, etc., which are also discussed in the paper. So yeah, that was the video about my thesis. I think we went on a bit long, but in overall we saw the method I used, the things, the findings I found, and hopefully it gave maybe inspiration or a more clear view on what tradable factor risk premia are, and how to calculate them, and how to construct your own research based on this, or go with further research directions. So thank you, and yeah, thank you, and see you.